How do quantum effects influence water's hydrogen bonds? Imagine tiny particles so small that they don't follow the usual rules of physics. That is what happens with protons in water molecules. These quantum effects change how water molecules stick together and move. Hydrogen bonds are the connections between the hydrogen atom of one water molecule and the oxygen atom of another. These bonds are not static. They are always forming and breaking. Quantum mechanics makes these bonds even more flexible and lively. Protons in water do not stay in fixed places. Instead, they can fluctuate and sometimes even tunnel through energy barriers. This tunneling means protons can appear on the other side of a barrier without climbing over it, making hydrogen bonds switch partners faster. Because of these fluctuations, protons can sometimes get closer to neighboring oxygen atoms than classical physics predicts. This can cause tiny, temporary events where a proton transfers from one water molecule to another, called autoionization. These events are rare but important because they influence water's ability to conduct electricity and react chemically. Quantum effects also help water molecules rotate and reorient more easily. Tunneling allows protons to overcome energy hurdles that would normally slow down these movements. As a result, hydrogen bonds can flip or rearrange at higher rates, especially in confined spaces like tiny pores or biological channels. This increased flexibility helps explain why water can change its structure so quickly and why it behaves differently under various conditions. Another way quantum effects influence water is through charge sharing. When hydrogen bonds form, electrons are not always shared equally. Quantum mechanics allows for some charge transfer, which makes hydrogen bonds stronger or weaker depending on the situation. This charge transfer impacts properties like water's high surface tension, its ability to dissolve many substances, and its unusual density behavior when cooled or heated. These quantum influences are vital for understanding water at the molecular level. They help scientists create better models to predict water's behavior in nature, biology, and technology. For example, in nanoscale systems like filters or catalysts, quantum effects determine how water moves and reacts. They also explain why heavy water, which has deuterium instead of hydrogen, behaves slightly differently due to changes in quantum tunneling. In essence, quantum effects cause hydrogen bonds in water to be more dynamic, adaptable, and interconnected than classical ideas suggest. This makes water a unique and fascinating substance, with properties shaped by the strange rules of quantum physics. Understanding these effects helps us see why water is so essential and versatile in our world.